a capacitor, we use a simple value called capacitance to describe it. So once I have defined a capacitance, we will talk about two particular cases. One is I have a single conductor. A single conductor can also serve as a capacitor. Or we can have multiple conductors to serve as a capacitor. But in the end, I want to emphasize the strategy in evaluating capacitance. And if you still remember, we started with transmission lines, right? A lot of people ask me why I teach transmission line first. Well, the first information is we only need to have scalar processes, right? We don't need to analyze vectors. And the second is, in transmission line, if you still remember, the lumped element circuits are comprised of resistors, capacitors, and inductors. But in there, you just took capacitors, inductors, just willingly, but you don't really know how to calculate the capacitance or inductance for a given transmission line geometry. So the very reason I want to start with transmission line is I give you pretty much a full picture, and then we can nail down the problems one by one as we progress towards the end of the semester. Okay? So if luckily by the end of today, I can show you how much you have improved yourself. All right? Okay, the definition of capacitance is the amount of charge divided by the potential set up by these charges. Okay, so what does that mean? Well, let's take a look at a single piece of conductor. Okay. Again, we're dealing with a perfect conductor, so no field allowed inside and no charges are allowed inside the conductor. But you are free to have depositions of charges on its surface. From Coulomb's law, we know that a single charge can set up its own E-field pattern, and if you perform the negative line integration, you have electric potential. So the amount of charges you deposit on the surface of the metal actually gives rise to a total electric potential, right? So when you have charge, you have potential. So the next question is, well, if you have a friend who's very naughty, so now you have 1, 2, 3, 4, 5, 6. Now you have 6 charges, right? So the 6 charges together gives rise to certain electric potential. And your friend is donating another 6 charges. And he's asking you, well, if I place these charges, identical charges, very close to your original charges, what is the resulting potential? So this is actually a test to how your metal behaves. So in the ideal case, if you double the amount of charge, you pretty much double the potential as well. Right? This makes sense. Okay? So what happens if you triple the amount of charge? Do you need to calculate again? In the ideal case, you triple the amount of charge, you triple your electric potential. Right? Because you are depositing charges onto the same metal. And that metal is acting like a capacitor. So the physical meaning of capacitance is thus, for a given material with a given geometry, remember, material and geometry, these are the two keywords. When we're dealing with capacitors, it's crucial to understand everything changes once you change the material being used or the geometry being used. Okay? So basically, the capacitance, a single value, tells you whenever you have decided what material to use to fabricate the capacitor and in what geometry. Once you fabricate this guy, it has a unique way to present itself. In the way, if you have developed certain electric potential, that electric potential needs to have how much charge. Or otherwise, if I deposit this amount of charges onto this capacitor, it will give rise to certain voltage value, potential value. Okay? And that unique property does not depend on how much charge you deposit. So once you fabricate the capacitor, you have determined its material, its geometry, that capacitance value is held as a constant. Okay? So it does not matter you deposit the charge amount of Q or 2Q. Because whenever you increase the amount of charge, it increases the voltage as well. Okay? So the capacitance value is only a character of the material and geometry. Once it's decided, it's done. Right? So if we have a simple metallic sphere, a single one, okay, with an inner radius of B. So if I deposit lots of charges onto it, okay, or just a single charge, but now it's uniformly distributed, so this sphere surface is having a uniform surface charge density. So for this guy, what is its capacitance? This is a perfect metal molded in the form of a sphere with radius B. So material is determined, geometry is also determined. Then it should have its unique capacitance value. Right? So how to analyze it? Well, we know that total charge of Q is deposited onto the surface, right? The surface area is 4 pi b squared. So we actually know how to calculate this uniform charge density. Okay? So basically, Q divided by 4 pi r squared, if you're away from it, that's using Gauss's law, right? And we know the voltage. This is nothing new. We talked about it already. Okay? At R equals B, this is where your potential maximum is, right? And that is defined as V0. So all we're trying to seek is, well, we know the total amount of charge is Q, but we're looking for what is the resulting electric potential. being contributed by this charge onto the surface in a uniform way. Okay? So all we have to do is we take Q and divide it by V0. And that is the definition of capacitance. So that is 4 pi epsilon 0 B. Starting from this point and on, whenever you try to derive the capacitance value, you always have to bear in your mind your result should somehow show the dependence of material and geometry. Okay? So look at the simple expression. It is correct indeed, but where is the material response showing up? Where? Right now, we don't really have a way to express the change of material. Well, the perfect metal cannot be replaced, right? Ideally, you don't want to use other things to serve as a capacitor, but something you can change is the ambient, the environment. So in this derivation, what have we assumed? Epsilon 0 represents vacuum. So currently, this metallic sphere is held in vacuum. So if you want to change its capacitance value, all you have to do is immerse it into another medium. Do you need to recalculate the mathematical form of the resulting capacitance? You don't. All you have to do is you add epsilon r, right? So if you immerse this in water, in sugar, in salt, in glass, you don't need to go over the derivation again. All you need to do is incorporate the corresponding relative permittivity of your ambient material. Okay? So that takes care of the material dependence. What about the geometrical dependence? Take a good look. I mean, well, epsilon 0 times epsilon r is the absolute permittivity, and that takes care of the material response. What else do you have? 4 pi b. To your surprise, 4 pi b, the fact 4 pi b is actually telling you you have a capacitor in the form of a sphere. Do you know why? So in the future, once you derive something 4 pi times something, this b is the radius, right? Where is the fact it's 4 pi coming from? You have a sphere with a radius of b, right? So the surface area is 4 pi b squared, right? So this 4 pi is coming from the fact your current geometry is a sphere, and this b is taking account of its radius. Okay? If you don't believe me, let's continue. Alright, so we've taken care of the single capacitor, a single conductor capacitor. In our daily lives, usually capacitors are made with multiple or dual conductors. The easiest one, which we will analyze later, is having 2 parallel plates of conductors. But there are capacitors molded in different geometries. If you open up your motherboard for your PC, you can see a lot of these guys. So these are molded in a circular geometry, and they fill with some kind of water and liquid, right? So if your motherboard breaks down, usually it's because of leakage in your capacitor. But at the same time, you see a lot of these guys. So these are ceramic capacitors, but they all serve as capacitors, a way to store electrical energy, and later you will understand the capacitors are actually frequency-dependent filters, right? So what happens if we have two conductors? It also functions like a capacitor, right? And for these two conductors, you connect it with a battery. Okay? Now, usually what it does is when you connect the battery, you have positive charges deposited on the end of your positive. And you have negative charges deposited over the electrode connected to the negative end. Alright? So once you can draw this charge distributions, then you can draw the corresponding E-field line distributions. Okay? So if you know the E-field distribution, and then you can calculate the resulting electric potential difference. Okay? But my question to you is, at this point, if these two conductors are serving as a capacitor, if I remove this battery, will its capacitance change? Think about it. In another way, I'm asking, for a given capacitor, do I really need to connect it to a battery in order to serve or define it as a capacitor? Really no, because capacitance exists even though you do not connect it, right? If you understand the definition of capacitance is only to say once you fabricate this guy, it's having its own material and geometry, it has its own capability to draw charge and develop electric potential difference, and that's it. So even though it's not connected, you can still label it with its capacitance value.